and we're going to try to talk about odds at the same time. So it could have been split up into two lessons. I'm going to try to combine it into one. I think they just fit together nicely. That's why I do it that way. Your practice book that I'll hand you, you'll notice it's split up into two sections. It'll be probability and then odds. So most of you guys have probably talked about probability or heard probability at some point in your life. In math, it can be a little bit different than what you're used to. So probability is just a mathematical way of showing the chances that something are going to happen. And that's all it is. So it's trying to almost predict the future is what it's doing. To understand probability and the questions that we're going to be dealing with probability, there's just some terms that you're going to have to get used to. The first term is trial or experiment. You might hear either of those words. An experiment is just multiple trials, but that's just you doing something. So, for instance, flipping a coin. That could be a trial. An experiment could be flipping 3 coins. Okay. Another type of trial you'll see is rolling a dice. So if you roll a die, that would also be considered a trial. Maybe you're going to roll a die and you're going to flip a coin. And you're going to be getting all these different results. These are just different types of trials or experiments. So if you ever see something like, what's the trial? The trial is just what you're doing. Usually in this class, you're rolling a dice, you're pulling a card out of a deck of cards, something very simple. Second term that you're going to have to know is outcome. The outcome is the result of your trial or experiment. So for instance, if my trial is to flip a coin, the outcome's either going to be heads or tails. So if you go, trial was tossing a coin, outcome was heads. If the experiment was tossing a coin and rolling a dice, then my outcome could have been I got heads and then I got rolling a 6. So that would be my outcome from my experiment. So if anyone ever asks you for what's the outcome, they're just trying to figure out what happens after you do your experiment. Sample space. A sample space is all possible outcomes. So for instance, if I flip a coin, what possible outcomes do I have? Heads or tails, one or the other, right? So that would be my entire sample space. I'm either going to get a heads or I'm going to get tails. One or the other. In my other experiment, the sample space is actually pretty large. So if I had an experiment of tossing a coin and rolling a die, well, all my possible outcomes is I could get heads and then a 1. Or I get heads and then I get a 2. I get heads and then a 3, heads and a 4, heads and a 5, heads and a 6. And you could also get tails and a 1, tails and a 2, tails and a 3, tails and a 4, tails and a 5, tails and a 6. So your sample space for an experiment like that would be significantly larger. I like to think of sample space almost as like your universal outcome, right? Or your universal set when we talk about Venn diagrams. A sample space just covers everything. Yeah.
In the second example, within like those squiggly brackets, you've got the H1, comma H2, like would that be how you grade it?
Yeah.
Within the brackets, the set of brackets, would that be?
Yeah, the curly brackets means you're talking about a sample space, and then the individual little like round brackets are talking about one possible outcome. So it's like this is a possible outcome in the sample space. This is a possible outcome in the sample space, and so on and so forth. So these are all just possible outcomes within the curly brackets, which is in the sample space. All right, there's some other things we're going to have to see, and we've seen things similar to them. When they represent probability of an event, so it says, to represent probability of an event A, we write it like this. So it'd be P bracket A bracket. That would just mean the probability of event A. That's how you read that. The probability of event A. And it's written right in there for the notes already, but if you want to highlight that, that's a good idea. Most of the time, probability is represented as a decimal or as a fraction. Every once in a while, they'll change it to a percentage, but we really try not to. Because what you see is decimals and fractions. So that's how we're going to keep our answers for this entire unit. If you get a probability of 0, that means there's no chance of something happening. If you get a probability of 1, that means it's guaranteed to happen. So it says that in here. It says 0 represents an 0 probability of happening. So 0 represents no chance of it happening. And 1 represents an event guaranteed to happen. So if you have a probability equal to 1, that's a guaranteed thing that's going to happen. All right. How to calculate probability. This is probably the most important thing to understand. To calculate probability, you get this formula given to you. So it'll say P of A is equal to the number of favorable outcomes divided by the total number of possible outcomes. That's how I like to phrase it. The reason why is it just makes sense to me. So you put what you want to happen and how many of those things could happen on the top, and you put the total number of things that could have happened on the bottom. Kind of like when you write a test, right? And you write a test that's out of 10. If you get 9 questions right, that would be a favorable outcome. So you got 9 on the top. The total number that you could have got was 10. 10 went on the bottom. So for probability, saying total number on the bottom, what you want to happen on the top. Number 1, example. A fair die is rolled. Anytime you see a fair die, they're talking about 6 sides. And it's not weighted in any possible way. So it'll always be evenly distributed. What is the probability of rolling a 6? So we're going to say P of A, we're going to call this event A, so let's say that, equals. How many possible outcomes do we want to have happen? There's only one possible outcome we want, a 6. It's the only possible outcome we're looking for. So on the top, the number of favorable outcomes is 1. Divide by the total number of outcomes that could have happened when we rolled that die was 6 possible outcomes. You could add a 1, a 2, a 3, a 4, a 5, or a 6. So the total number of outcomes was 6. The probability of rolling a 6 would be 1 over 6. You could put that into a decimal with 0.111. These are the equivalent answers. That's a pretty basic question. If your diploma had that question, you should be super happy. It's not going to have that question, though. Number 2. A card is drawn from a standard deck of cards. All right, we're going to talk about a standard deck of cards, and I suggest that maybe if you don't know cards very well, you write some of this stuff down. So, a standard deck of, pardon? There's 52 cards. That's good. That's a start. So,
I'll bring down one brother to pick up.
The first time, right? That's how I learned it. There's 52 cards.
13.
Yeah, we're going to start figure number first, and we'll figure our way down. Out of those 52 cards, 26 of them are red. 26 of them are black. Out of those 26 that are red, you have 13 that are hearts, and you have 13 that are diamonds. Out of those 26 that are black, you have 13 that are spades. That's always fun to try to draw a spade. There we go, that's the best spade I've ever drawn on. Oh, you don't love it? It should just be a pointy guy. And then 13 of them are clubs. And clubs is even the other. So that was G's making clubs. Club kind of looks like a clover. Things you also need to know is there's 4 of every number. So there's 4 cards that are 2 through 10. So there's 4 2s, there's 4 3s, there's 4 4s, there's 4 5s, 4 6s, so on and so forth. You also need to know that there's 4 of the face cards. That's jacks, queens, and kings. And aces. Yep. Yeah, this will be, so on your diploma, like if they do a card question, you'll have to know all those things. So if they say, what's the probability of drawing a black card, you have to know that there's 26 black cards out of the 52. It won't be given to you on a formula, so you do need to know these things. That's why I was like, you might want to write these down. Yes, sir.
Not to fight the system, but why does our grade depend on our knowledge of a card?
Yeah, the reason they do cards is they assume, which I don't think they rightfully assume, that everybody knows a standard deck of cards. It's also like a basic thing to discuss when doing probability. So the other things you might see is like, actually I think recently they've started telling you information about the deck of cards. So they'll say it's a standard deck of cards with 13 diamonds, 13 clubs. So that I think they've actually tried to fix that a little bit. But they just assume that a standard deck of cards is something that everybody should know. Kind of like when they say a die, they assume you know that there's 6 sides. Right? That's just your standard dice. And that, whether that's fair or not, I'm with you. It kind of sucks if you don't know a standard deck of cards. That's why I'm taking the time to definitely write it out and point it out. Yep. No, that'd be pretty cool though. You actually try things in it. Alright. A card is drawn from a standard deck of cards. What is the probability of drawing a heart or a club? So we're going to say probability of drawing a heart or a club. So probability of event A equals. How many favorable outcomes are there? How many hearts are in that deck? There's 13 hearts. How many clubs are in the deck? Another 13. Divided by how many total things could have been drawn out of the deck? 52. So this would be 26 divided by 52. That would be your probability of drawing hearts or club. Yes, yeah.
How many jack or jokers are there?
No jokers.
No
No jokers. This is a really good answer. Probably not the answer that would be on a multiple choice test. It simplifies. So you put that in your calculator, your 26 divided by 52, and then you'll math frac. That's just 1 over 2. It's also 0.5. So one of these two answers would be your best answer on this test. Either one could show up. 26 over 52, probably not going to show up.
It'll probably show up to distract you.
Yeah, like if it's a like best answer or something.
Like it'll probably say 26 and 52, or then 1/2 and then 2 other random.
Yeah. So make sure you're trying to pick the best answer possible. That's possible. What you want to happen divided by what could have happened. Complementary events. A complementary event is something we've actually already kind of talked about. Oh, do you need that?
Yeah.
Yeah, for sure. A complementary event is the opposite of something happening. So for instance, if I said, I'm flipping a coin and I want tails, the complement to tails would be getting heads. It's the opposite event. Okay? So this slide has examples of that. So a complementary event is just the opposite of something happening. If you read this one, it says, our example before was rolling a 6. The complement to rolling a 6 would be not rolling a 6. You can also say rolling a 1, 2, 3, 4, or 5, right? That's still the opposite. It's just that's a simple way of saying it. Not rolling a 6. What is the probability of not rolling a 6? Not rolling a 6 would mean favorable outcomes are 1, 2, 3, 4, 5. So there's 5 favorable outcomes divided by 6 possible outcomes. What's the probability of rolling a 6 again? 1 over 6, or 0.11111. 5 over 6 is the not rolling a 6. 1 over 6 is the probability of rolling a 6. Complementary events will always add up to equal 1. The reason being is if your event doesn't happen, then the complementary event had to have happened. And it's the only thing that makes sense. If I didn't roll a 6, then I had to have rolled a 6. So if I took the probability of not rolling a 6 plus the probability of rolling a 6, it has to equal 1. It's the only thing that makes logical sense. There's nothing else that could have happened. That gives us a formula. The formula is right here. It says P of A plus P of A with a little apostrophe, which means not A, equals 1. That formula will be given to you on your diploma. As of now, I'm saying that. I seem very confident on that. This is not on your formula sheet. Let's just make that clear. And Steve's question of how would they ever ask us a question that makes sense, they could give you two events. They could say the probability of event A equals what? The probability of event B equals 10 over 6. Are these complements? Is it possible that these could be complementary events? So you would have to test, if I took probability of A plus the probability of B, would it equal 1 in my calculator? And in this case, it would equal 1. So it doesn't look like it would, but this is provided 1 over 2. 1/2 plus 1/2 equals 1. So these could possibly be complementary. If it had been some other fraction, like 2 out of 5, then they couldn't possibly be complementary because they don't add to be 1. We don't do a lot of complementary events, just compound events we do a lot of. And compound events is when something happens and then something else happens. So that's the stuff you're most likely going to see and the stuff that you should be able to kind of nail down by the end of this unit. The first question is a compound event. It says 2 coins are flipped. What is the probability of getting both tails? So we're going to do this incorrectly the first time, and then we're going to do it correctly the second time. So most people know that if I take a coin and I flip it, and I take another coin and I flip it, there's 3 outcomes. I could get heads and heads. I could get heads and tails. I can also get tails or tails. No disagreement. Correct? Those are the 3 possible things I could get unless it lands on its side, which is going to happen. We want both tails. So how many favorable outcomes are there? There's only 1 favorable outcome. How many total outcomes was it? There was 3 total outcomes. So I could guarantee you if this was a test question, that would be one of your multiple choice answers. This is not correct. The reason it's not correct is because that's not the proper sample space. The sample space is not heads, 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 tails, 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 because you could get heads and tails 2 different ways. So the best way to do these questions is by using a tree. And I always do this, coin 1. And I write out the possibilities for coin 1. So what could coin 1 be? Heads, tails. Then I have coin 2. Once I get heads, coin 2 could be either heads or tails. Once I get tails on the first coin, my second coin could either be heads or tails. This properly shows your sample space. because each branch is one possibility. So my third column is outcomes. One possible outcome is I get heads, and then I get heads for H, H. A second possible outcome I could get would be heads and then tails for H, T. A third thing I could get is tails and then heads for TH. And the last thing I could get is tails and then tails. So even though getting a heads and getting a tails is the same thing as getting a tails and then getting a heads, like it's the same result, there's actually two different ways we could have got it, meaning that there's more likelihood that we get that. So you have to include that in your sample space, because there's two ways you could have got it. The proper answer to this question would be 1 out of 4. Because there's 4 different outcomes that you could have got. And there's only one of those 4 that's favorable. Probability in this whole unit is a unit that's really easy to feel like you got every question right, and then you actually got every question wrong. Because the mistakes are simple. It's easy to look at something like that and really quickly go, heads, tails, tails, tails. 3 situations, done the question. So it's important during this unit to just take your time, learn what we've learned, remember what we learned, and then try to do it. All right, another example of this happening is you can have a coin that's flipped and a card that's stand the deck. What is the probability of getting heads and getting an odd number? This one's going to be a little bit trickier to figure them all out, isn't it? Let's try this using our tree. So, you got a coin. You could get heads. You get tails. Yeah.
Don't count aces as long.
Don't count aces. It counts as a base card. After I get heads, I'm going to draw from the deck of cards. I could get heads, and then I could get a 3. Remember, 1 is not in a set of cards. I get heads, and then I get 5. I get heads, and then I get 7. Or I get heads, and then I get 9. For tails, the same situation could happen. So I get tails, and then I could get a 3. Tails, and then a 5. Tails, and then a 7. Tails, and then a 9. So, we didn't want to do our tails, so I'm going to erase that. I just explained that to you guys so it's not on that video forever. We didn't want to do our tails because tails isn't a favorable outcome. Right now, all we're calculating is our possible favorable outcomes. And tails was not a favorable outcome, so I screwed that up. What this is going to show you is all of your possible favorable outcomes. Your favorable outcomes could be heads in this, heads in this 5, heads in this 7, heads in this 9. No, yeah, you don't have to worry about that. We're going to just pretend that there's only like 1 of each. Make life easy. So we're pretending there's 1 of each card, not 4 3s or 4 4s or anything like that. In the future, we'll be doing that though. I think that's in 2 days. You're like, oh, wonderful. These are your number of favorable outcomes. How many favorable outcomes were there? That's 4 favorable outcomes. You need to then divide that by the total number of outcomes. And again, we're pretending that there's only 1 of each number, right? So you could have drawn a 2, a 3, a 4, a 5, 6, 7, 8, 9, 10, or Jack, King, Queen, Ace. So there's, how many is that? That's 13, right? Yeah. 13 things you could draw out. It's a lot of cards. If we were trying to make a tree with 13 different things, and then you're going to do it off of heads and off of tails, that's a huge tree. It's doable. If you had the right room for it, you could do it. But what we're going to do is we're just going to think about it for a second and see if we can't solve it and use a little bit of logic. So if this were to be a tree, if I had heads, how many branches would then have to come off of that to create all the possibilities out of the cards? There'd be 13, right? So there's 13 outcomes that include heads. How many outcomes include tails? Another 13. So how many possible outcomes are there? 26. If you did a massive tree, it's doable. I'm not saying you couldn't use our method from before. You definitely could. It's just going to be pretty darn big. Your outcome or probability would be 4 out of 26. That probably isn't going to be the answer that's in your answer key. What would be the answer in your answer key? 2 over 13. How do you get that? Divided both numbers by a common number. You could also put in your calculator. 4 divided by 26. Math, frac. That'll give you 2 out of 13. The tree could get big and you could do it. Or you can try to think through it to make it go a little bit faster. Your choice. All right. We have another question here. I want to give you guys the opportunity to do this one on your own. Okay, so you got 2 coins are flipped and a spinner with areas red, blue, green, and yellow are spun. The best way to do this question, I'll start you off, like a tree. So you have coin 1, coin 2, and then spinner. Then you should have your outcomes. So try to make a tree that represents this scenario. Okay, so if we build this question together, what I would have done is coin 1, coin 2, and then spin. After I get coin 1 as a heads, coin 2 could potentially be heads or tails. So you have to build off both possible realms. And then after I get heads and then heads again, I could potentially get any of the 4 colors. After I get heads and then tails, I could get potentially any of the 4 colors. And you do that all the way through for every possibility. You should come out with 16 total outcomes. Some of them might be the exact same, but there should be 16 total outcomes. So that's your total number of outcomes. Now to answer the questions A and B, we have to figure out what our favorable outcomes are. So A says, what is the probability of getting heads, tails, and blue? So you need to look through your list, find out where you have heads, tails, and blue. There's 1, and there should be a 6. There's 2 possible outcomes that go heads, tails, and then blue. This one's backwards, it's tails, heads, blue, but if you looked at it, it would be the same result. That means we have 2 out of 16, which is just 1 out of 8, which is 0.125, I think. If you try it again, so B says, what is the probability of getting both tails and green? Well, both tails is pretty rare. It's only these 4 over here. Both tails and green is better. So there's only 1 favorable outcome out of 16. Change that to a decimal, it's 0.0625. Can we try it? Here's sure. Those are compound events that can be done using trees. Now, trees aren't the only way to do these things. Sometimes there's better ways. This question is an example where I probably wouldn't do a tree. I would do a different method. And that's because there's two things and they're both dice, so I find it easy to make a chart. And that's what I do for this thing. So it says a red-sided die and a blue-sided die are rolled. What are the possible outcomes? You could do a tree. You could do red die. Don't write this down. And you could do 1, 2, 3, 4, 5, 6. You do blue die. And then each one of these 6 is going to have 6 off of it. And you can tell that that thing is going to be like massive, right? And it's going to get a little bit crowded and a little bit confusing. So a tree isn't the best way to organize things when there's a whole bunch of outcomes, like multiple dice being rolled. When a coin's being flipped, there's only 2 outcomes, makes a tree pretty easy. In this situation, what I would make is a chart. And I would make the top be the red dice. And I would write out all the possible outcomes of that red dice. And then I'd make the side my blue dice. And what you've done is you've created a table, hopefully. The trick is to line straight enough with the box cells.
So should we be drawing this P?
Yeah. Yeah. Draw whatever way you need to. But this grid is going to be a nice, organized way of figuring this question out. Yours should be a lot neater than mine. All right, let's. This chart's doing the same thing that our trees were doing. It's just, to me, more organized once you fill it out. It's just a little grid, easier to read. I'm going to fill in each one of these spaces on the grid. When I read it, I'm reading the top thing first, the second thing, to the side thing second. So my first little grid would be 1, comma 1. The next one would be 2, comma 1. You see the trend I'm going to do? So you're going to fill out all those boxes. This would be 3, comma 1, 4, comma 1, 5, comma 1, and 6, comma 1. And if you just keep this trend going, you'll be able to fill these out in no time. Some people will try to find ways to do these things in their head. I highly recommend against it, because odds are you're going to miss something. Or if you just try writing them all out by hand, typically you miss something. And that's just not a good sign. Anyways, so what we did in that grid is we created all of the possible outcomes. And there's a lot of them. If you counted out, how many possible outcomes are there? There's 36. So how many points are in the sample space? There's 36 points in that sample space. These are all the possible events that occur. You could roll 1 and then a 1, a 1 and then a 2, 1 and then a 3, all the way up till 6, comma 6. C says list the event the same number appears on both die as a subset of the sample space. So the event that they want to have occur, the same number appears on both die. So we're going to write out all the possible times that happens. So curly bracket to say it's a set, and then all the events are going in round brackets. 1, 1 is possible. 2, 2 is possible. 3, 3 is possible. 4, 4 is possible. 5, 5 is possible. And 6, 6 is possible. The curly bracket says this is a set. The little bracket says these are events that happen in that set. So that's why there's a difference in brackets. D. What is the probability of the same number appearing on both die? To calculate probability, you want to do the total number of favorable outcomes. So how many favorable outcomes are there? There's only 6. Divide by how many outcomes are possible. So that means 1 out of 6. Do we simplify that? 0.111. The probability of the same number appearing on both dice is 1 over 6. What is the probability of different numbers appearing on both dice? So if you went through and counted, you could. You could go through and count every time that 2 different things happen. Or you could use the complementary set to help yourself out. So if you're not getting the same number on both die, that's the opposite of getting the same number on both die, correct? Complete opposite, complementary. So that means if 6 was possible before, we need to be able to add up to 36. It's going to be everything else. It's going to be 30 out of 36. It's all possible other events. And again, we could use our little thing to prove that these are complementary by saying that equals. The green part you don't need to do. It's just showing that, yeah, these are complementary. We did it right. Okay, you got a couple months. You got a couple months to get ready.
Gregor was fun there, so I don't feel as bad.
All right, whatever.
What was the probability like?
Higher than what I would guess. Yeah.
Okay.
You good? All right. Odds. Odds are another way of describing a chance of something happening. They are usually written as ratios. Odds and probability, they go hand in hand. And you're going to be able to bounce between the two. Example 1. What's the probability of rolling a 4 on a 6-sided die? 1 favorable outcome divided by 6 possible. 1 out of 6, that's the probability of that happening. If we wanted to discuss that as odds, you instead write it as a ratio. And the ratio would say, we could say that the odds for rolling a 4 are 1 to 5. The reason why we choose numbers 1 to 5, odds for rolling a 4, that means there's one thing that we want, which is rolling a 4, and there's 5 things we don't want. So that's 1 to 5 odds. One thing we do want to have happen, 5 things we don't want to have happen. They don't always talk about odds for, sometimes they talk about odds against, especially if you watch sports. They always talk about odds against. So you could also say that the odds against rolling a 4 would be 5 to 1. Because there's 5 things that you aren't for and 1 that is for. So when you're doing odds against, you're putting the thing that you didn't want to have happen first, and that you do want to have happen second. Odds are represented using a ratio. From the questions above, we figured out that there's these 2 formulas. So odds in favor of an event equals the number of outcomes for A, ratio, a little colon, number of outcomes against A. The odds against event A would be number of outcomes against A that you didn't want. and then colon number of elements you did want to have happen that were for it. Example. What are the odds of rolling a 1, a 2, or a 3 on a 6-sided die? 6-die side. How many things possibly could happen that we want to have happen? 3 possible things could happen. You get a 1, a 2, or a 3. So we go 3 colon. How many things could happen that we didn't want to have happen? 3. You get a 4, a 5, or a 6. So your odds would be 3 colon 3. That means 3 things we did want, and there's 3 things we didn't want. And that's the odds of it happening. 3 colon. When you get numbers that are the same, you might hear it said 1 to 1. You might also hear it as 50-50. Because what you really have is you have an even odds. And that's what it goes in this blank. When this happens, we call it even odds. If you're a gambling human being, which I tend to be, for instance, I like to gamble Slurpees on Oilers games. So if me and McGregor went to gamble and I said the Oilers will beat the Flames, and if I win, I'll give you a Slurpee. If you win, you give me a Slurpee. We're saying the odds of that game would be 1 to 1. They'd be even odds, right? He would get the same prize I would get. We're saying it's a fair game. Realistically, the odds are way in the Oilers' favor. It's a good bet for me.
That was a weird What's the next one?
Between them, the next one that matters, October 4th.
I'll bet it.
Okay. I used to bet with Aaron Pickering, but he's graduated. Can't.
What's the Oilers win?
Everyone's a 2. Keep this looking up. All right. Example 2. Mr. Kennedy's high school teacher told him he had even odds of graduating high school. What is the probability that Mr. Kennedy would graduate? So what's the probability I would graduate, according to my teachers?
He said he wouldn't graduate.
Let's wait. So the odds would be 1 to 1, because he said I had even odds. But the question was, what's the probability that I would graduate? So now you need to turn it, back into a fraction. So this is odds. Turning that into a fraction, you need to go favorable outcomes divided by total outcomes. Favorable outcomes was 1. Me graduating. Total number of outcomes was 2. Either I graduated or I didn't graduate. According to him, that was the odds.
Didn't he say working?
Yeah, he gave me 0. Example 3. How this can get a little bit more tricky. A few months later, picked up my game, Mr. Kennedy was told that the probability of him graduating becomes 0.65. So it's gone up. That's good. What were the odds in lowest terms that Mr. Kennedy would graduate? It's really hard to go from decimal to odds. So instead of going from decimal to odds, go decimal to fraction to odds. That's a lot easier. So in your calculator, you're going to go 0.65 and you're going to go math fract. And that'll tell you the fraction in lowest terms that is equal to 0.65. Somebody do it? 13 by 5.
20.
Thank you. From here, we can figure out what my odds were of graduating. Odds in favor of me graduating. The first number is going to be what we want to have happen. So there's 13 of what I want to have happen. Colon. The second number is how many things are me not graduating or not having this thing happen. 20 is the total number of outcomes. the total number that you didn't want would be 20 minus the number that you did want. So 13 to 7 would have been the odds of graduating with a 65% probability. So you see how this can get confused pretty quick when you start jumping around things. Odds are what you want versus what you don't want. Probability is what you want divided by everything that could happen. This is what odds looks like. Odds are often used in sports, which is why I brought up a sports analogy. And you'll hear at the beginning of any season, if you're a sports fan, the odds of you winning the Stanley Cup, or the odds of you winning the Super Bowl, the odds of this, the odds of that. And they just released the odds of people winning the Stanley Cup. So these are actually the odds that Las Vegas has decided for each team. But it's not odds for you winning the Stanley Cup, it's odds against you winning the Stanley Cup. So that's also important to understand. That word against is very important to this question. If you miss that word against, you're going to get it all backwards. They list all teams, all 30 teams. I've only listed off 7. Okay? Yeah, this would say that I didn't know of these. So this would say the Pittsburgh Penguins odds are 9 against for every 1 that's favorable. The odds against the Oilers winning would be 10 against for every 1 that's favorable, which would be them winning the Stanley Cup. The Capitals would be 10 and 1, just like the Oilers. And down here, the one that's the worst, the Calgary Flames, theirs is 33 against for every 1 that would happen for them winning the Stanley Cup. So if you were to read this chart and you were to figure out which team is most likely to win the Stanley Cup according to these odds, your answer would be the Pittsburgh Penguins. If this had been odds for, then your answer would have been the Calgary Flames. But this is odds against. So for every 9 times the Penguins don't win the Cup, they'll win it once. For every 10 times they don't win it, they'll win it once. It's kind of how you can think about it. So it's a lot more likely that Dallas will lose than they'll win. Question B, which team is least likely to win the Stanley Cup? I put that question in the first one. The Calgary Flames. And question C, describe what is meant by the Oilers' odds 10 to 1 against. That means that, you can describe, you can write it out if you want. I'm going to describe it verbally. The odds 10 to 1 against mean that for every 10 times they don't win, there's a 1 chance that they will win. And you can write that in any kind of sentence you want, as long as you're understanding that the 10 is not them with the cup, and the 1 is them with the cup. They will win 1 for every 10 that they lose.